Okay, our first talk this morning is Ben Bakker. We talk about the geometric Andre Grothendieck period conjecture.
Great, thanks so much for the introduction and for the invitation. And happy Groundhog Day. I feel like that's appropriate for people who have seen this talk many times. Okay, so the Hodge conjecture is conjecturally sort of one way that Hodge structures are supposed to see geometry. And I want to talk today about a slightly different way that sort of Hodge structures are supposed to see geometry. And this is more via the transcendence of periods as numbers. Okay. So let's set things up. Let's take K, a subfield of the complex numbers. And X over K, smooth algebraic variety. Not so important that it's smooth, it just makes things a little simpler. And there's two natural sort of cohomology groups we can associate to X. The first is what I'll call sort of eddy cohomology. And by this I just mean, HI of the complex analytification of X with key coefficients, usual singular cohomology group. And this is a Q vector space. And it's the Q vector space of sort of Q forms on topological cycles, again in the sort of X with the classical. Okay. On the other hand, I can form a more algebraic object, the Ram cohomology. Okay, algebraic Ram cohomology. So now this is a K vector space. This is the K vector space of sort of Durand cohomology classes of closed K-rational algebraic forms. Closed K-rational algebraic. Okay, and so to any you have to be a little careful about what exactly you mean here. Maybe you have to allow some polls to get all the random cohomology classes, but whatever. In some way, shape, or form, all of the classes here come from K-rational algebraic forms. And there's a natural map, at least over C, which sends a Durand cohomology class represented by some K-rational form to the Q form on cycles, which just takes a cycle and integrates omega against it. So this gives me a map, again, after I tensor up with C. And this is an isomorphism by the Durand. So somehow, the sort of matrix of this isomorphism is just given by these numbers, these period integrals. And the principle I'm going to be talking about today is somehow that these numbers should be as transcendent, as algebraically independent as possible, unless there's sort of a geometric reason for them to be algebraic. Principle here, then sort of algebraic relations among periods, by which again mean these like numbers, should come from geometry. Okay, so let's make these ideas a bit more precise. And one way to do this is via what's called the Grothendieck period conjecture. Okay, so here's the conjecture. We have the Grothendieck period conjecture. Okay, so what does it say? it says, well, let's take a variety over the rational numbers. Okay. So on the one hand, we want to make sense of sort of how transcendental all of these numbers are, and how algebraically independent. And there's sort of an obvious notion for that. We just look at the transcendence degree of the field over Q generated by all of these periods. So I'll call these the periods of HIX. Okay, so you should sort of think of this field as like the field of definition of this comparison. So we're sort of measuring the transcendence degree of that field of definition. So that's telling us how algebraically independent these periods are, and sort of how do we make sense of sort of how algebraically independent we expect them to be from the perspective of geometry. Well, that's measured by the dimension of the motivic-Galois group of this homology. And I'll say some words in a second about what that means. The conjecture
is they tried to run.
Sorry. Well, I'm being a little vague here. By HIX, I kind of mean the package of information, this, and the comparison. Okay, and then this periods of HIX, I mean the matrix of this comparison. So literally these numbers for all k rational. And then the conjecture is that we have equality. Okay, so let's make sense of this object. So, you know, if you're not familiar with this, it's going to sound a little complicated, but it's actually not so complicated. Take your favorite sort of Tannakian category of motives over Q. Okay, so that's some kind of universal cohomology theory, sort of for varieties defined over Q. There's a couple ways to construct this, and you can sort of pick your favorite answer, and they will all give you the same motivic-Galois group. Nori has a particularly simple construction, or you can use sort of Blavatsky's theory, which doesn't directly construct this, but you can still get the motivic-Galois group from it. But anyway, the upshot is this is some universal homology theory. So a typical object is exactly something like HIX. Sort of objects of here specialize to sort of all different homology theories. So, you know, there'll be a functor to, you know, Q vector spaces that gives you that homology, or there'll be a functor to K vector spaces which will give you the RAM, or Q vector spaces in this case. K is Q that will give you the RAM homology. But anyway, the point is that this category, it being Tannakian, means that it's equivalent to representations of some pro-algebraic group. And that's what the motivic-Galois group of Q is. Okay, so via this identification, an object such as HIX, you know, corresponds to some representation of this group. Okay, so it corresponds to a representation rho from the motivic-Galois group. How does this work? Well, the representation is valued in you know, the group acts on the Benny realization of this. So it maps into, I think myself up wrong here. We go vertically. This is a representation rho that maps into GL of the Benny homology. This is the finite dimensional Q vector space. So that's what this object HIX corresponds to. And this group is just the image of this representation. And so this will surject on the subgroup, which I'll call G mot HIX, which is just sort of the image. And so that's what I mean by the motivic-Galois group of HIX. Okay, and then let me just say a few words about why this is sort of the correct object. Well, somehow within this category of motives, which is the same as the representation of this group, the smaller the image of the representation, the like more maps you'll have between tensor powers of this guy. Okay, and in this category of motives, if you have maps between representations, they come from geometry. Okay, so the smaller the image of the representation, the more sort of self maps you have between tensor powers. That means there's more sort of cycles inducing those maps, and those are giving you relations among the periods. Okay, so this is smaller than this is smaller, then the periods are more algebraically. Make sense? Cool. Okay, great. So this is a conjecture. A remark. I won't say it too precisely, but there is sort of an enhancement of this conjecture due to Kontsevich-Zagier. And I won't write it down precisely, but it somehow says that the only relations on the periods of algebraic varieties over Q are the ones coming from push-pull with respect to algebraic maps and Stokes theorem. Only relations are sort of push-pull and Stokes. Okay, so it formally makes sense. Okay, so this is a nice conjecture. It's slightly unsatisfying from a couple perspectives. Sort of from the perspective of algebraic geometers, maybe it's sort of restricted to talk about varieties defined over Q, so it has sort of a very arithmetic feel to it. From the perspective of like transcendental number theorists, there's only so many numbers that show up here that you're able to test the transcendence of. So notably, E is not supposed to be the period of an algebraic variety defined over Q, and so you can't sort of test transcendence against E, but transcendental number theorists are interested in E a lot. Okay, so that's why it's lucky that there's a generalization of this conjecture due to Andre. I'll call this sort of Andre Grothendieck theory of conjecture. And in fact, the statement is kind of clear, but that kind of belies how interesting the conjecture is. So let me write down the statement. Basically, the statement is, well, let's take any intermediate field.
So this, the conjecture relation dimension of this group. This is a Q algebraic group or what?
This is a Q algebraic group. Yeah, this is the Q algebraic group, and the dimension equals this. Okay, well, I should have said over here, since I have this whole motivic framework, there's no reason to only be talking about the motives that look like HI of a variety. You may as well just take any motive over Q. This conjecture sort of makes sense for any motive M. Place this with M, this with M, all the same definitions. Okay, so the Andre version of this conjecture is take now any intermediate field. And take M, a motive defined over L. Okay, then we still expect that we can still write down this sort of transcendence degree, the transcendence degree over Q about L adjoin the periods. And now we ask that this should be at least as big as the dimension of the motivic L. Okay, so let me make a couple comments. So first of all, the inequality is kind of necessary because now the issue is like L could be way too big to actually define the book. You could take some variety defined over a smaller field, then just take some bigger field containing it, then this side will get bigger, but this side won't. So you definitely need the inequality. But somehow this is the important inequality. In this special case, it's obviously a special case where you take L equals Q, the inequality in the other direction is sort of obvious. So the sort of real need to this conjecture is inequality this thing. Okay. Now, let me also say that this formulation is kind of cool because let's just think about what's going on. So suppose now we're interested in E. Okay, so now we can sort of adjoin E into our ground field. We can sort of test the transcendence of E against periods that are shown up in M. Okay, so this right-hand side is like completely algebraic. So as far as the right-hand side is concerned, that E is just an algebraic parameter. Somehow this conjecture is mixing sort of behavior of periods and families with the transcendence of numbers. That's kind of an interesting aspect.
So is there an L on the right hand side?
Nope,
Have a motivic group over L or something like that?
nope, just the absolute motivic group.
So wait, why is it point of L is not if M is one point over L?
M is over there.
Sorry, second.
But didn't we have to have motives over Q or over the define motive of the element?
Maybe. Wait a second. Maybe you're right. Maybe I do mean, I want to take the category motives over L. Yeah. I paused for a second because I'm in the, when I start talking about functional versions, there's like a relative motivic algebra that I want to talk about. That's not what we're talking about here. Okay. So let me just give a concrete example just to bring these ideas down to earth. Okay. So here's an example. Well, let's take some set of numbers in C star. Yeah, let's assume they're multiplicatively independent. Okay. By which I mean the sort of subgroup they generate has rank n. Okay. And the motive I want to consider is the one that sort of universally computes the relative cohomology of GM, comma, the subset of points, which is 1, alpha 1, all the way up to alpha n. Okay, so what is the field definition of this motive? Well, it's defined over L is equal to Q adjoin the alphas. Okay. Now, what are the periods of this gadget? Okay, well, this is an affine algebraic variety, so the Durand cohomology is like actually forms. And the only form that gives interesting periods is the logarithmic form, dq over q. Okay. dq over q. And what are the periods of dq over q? Well, of course, there's the loop around 0. And that gives me 2 pi I. And we're doing relative cohomology, so I am also looking at integrals along paths from, say, 1 to alpha I. Okay, so I also get log alpha I. For all I, we get log alpha 1. Up to log alpha n. Okay, and so this conjecture is saying, I can fit it down here, that the transcendence degree over Q of Q adjoin like all the alpha i's, and then 2 pi I, and then all the logs is bigger than or equal to something that's generally complicated to compute. However, Andre showed that for one motives, this group is precisely the Mumford-Tate group. Okay, so that's something we understand here. The Mumford-Tate group here is a GM extended by n copies of GA. Okay. So on the right-hand side, we get something that's n plus 1 dimensional. Okay. And in particular, if we kind of forget the 2 pi I, we're concluding that the transcendence degree let me even relabel some things. Let me call these logs beta I. Then I'm talking about the exponentials of the beta i's. We're saying that the transcendence degree of the field generated by these beta i's and their exponentials is bigger than or equal to n, which you might recognize as the Shannon conjecture. Okay, so this is a sort of big open conjecture in transcendental number theory. Just to give you a sense of how open it is, like for instance, if you take beta 1 to be I don't know 1 and beta 2 to be 2 pi I, you conclude that E and pi are algebraic. Okay. Still on that. Right? So this is good because it means that sort of this Andre version of this conjecture is kind of recovering some things that transcendental number theorists were already thinking. Let me also say, it also makes it sort of clear how much more powerful this version is than this version, because, the context of the Grothendieck period conjecture would be if, this motive were defined over Q. So in other words, it's restricted to the alpha I being algebraic numbers. Somehow a much weaker transcendence state, saying that if you have a bunch of algebraic numbers, then their logs are algebraic. Okay, so that's the sort of general picture for sort of the transcendence of periods as numbers. Now let's apply the functor of functional analogs to all three of these boards, because transcendence of numbers is hard, but transcendence of functions, we have a chance of proving some stuff. Okay, so what are the functional analogs of all these statements? Well, now we take as our base field not some subfield of C, but the complex function field of some complex algebraic variety. S, a complex algebraic variety. And we're going to take K to be the sort of complex function field. And once again, we're taking varieties over K. Smoothness is not necessary, but sometimes it's useful to think about that case. We sort of think of varieties over K as interchangeable with like actual families over S, up to shrinking S. Okay. So now once again, we have sort of Betty and Durham cohomology theories. So now Durham cohomology of X is a flat vector bundle on S. Algebraic flat vector bundle. Okay, and it's the flat vector bundle of sort of fiber-wise closed algebraic forms. Fiber-wise closed algebraic. Okay, so that's the Betty side. Let me erase this. What about the Betty side? Well, the Betty side is just the local system, the Gaussian connection. So by the Betty realization, I just mean Ri f over star x. Okay, so now this is a Q local system. So this is the Q local system of Q forms on like flat families of cycles. Okay, so this map still makes sense, except we want to integrate fiber-wise. And so, what we're actually doing is we're taking a fiber-wise closed algebraic form and associating to it the function which takes a flat family of cycles to the functions which are take the fiber-wise integrals. Okay, so now this integration map is defined. The output here is a complex analytic function. So this integration map is valued in sort of analytic functions. Okay, so the correct field to place here, over which this comparison becomes an isomorphism, is what I'll call Kn. And I really just mean this is the sort of field of holomorphic or meromorphic germs at some base point of S. Okay, so let's choose a base point. By Kn, I mean the sort of fraction field of the analytic local ring at that base point. Okay, so again, this is just germs of meromorphic functions at S naught. Here we're tensoring over Qx, the local system. And we're also tensoring over here. OS. Okay, and once again, this is a nice part. So again, pictures may be a little complicated, but the sort of point of this picture is that this comparison, this natural comparison that we have, its field of definition is naturally contained in the field of meromorphic function germs. Nice. I won't leave the principle there because the principle still holds. So now, with functional analogs, conjectures become theorems. Now, this Grothendieck period conjecture is a theorem. It's a published theorem of a U and an unpublished theorem of Corey. And what is the statement? Statement is, once again, let's take a motive over K. Okay. And we still want to take the periods of M, thought of as germs of holomorphic functions. We want to adjoin them to the function field of S. And we want to look at the transcendence degree over K. Okay, and the statement is that this is equal to the dimension of what's called the relative motivic Galois group. Okay, well, why is the relative motivic Galois group showing up on the right-hand side? Well, somehow, if I just take the Galois group of M, this is where I'm getting over there. Anyway, we can discuss it after. But somehow, like constant families of varieties still have an interesting contribution to this, right? Because those are interesting families. They're not the same in the category of motives. So I somehow want to mod out by like constant families of algebraic varieties. So that's what this relative motivic Galois group is doing. So what actually is it? It's pretty straightforward. So there's a base change functor from motives over C to motives over K. So by taking constant families. And a functor this way on representation category is a functor, a homomorphism in the other direction of motivic Galois groups. We have a homomorphism from this motivic Galois group to this one. Okay, and so the kernel of this you should think of as being the kind of relative motivic Galois group. And this group is just the image of this kernel in the representation corresponding to this motive M. Okay. We just spell that out. Remember, the motive M, which is an element of this category, is a representation of this. So in particular, we're getting mapped from the kernel into GL of the Benny realization of this motive. In other words, this local system. And the image of that representation is this. Okay, so let me erase this and keep the remark somehow. Because luckily in the functional setting, we actually know exactly what this relative motivic Galois group is. It's nothing more than the algebraic monodromy of the Betty realization. In other words, M, the Betty realization is the local system over S, and this is just the algebraic monodromy. This is the algebraic monodromy of Betty realization, which is a local system, but by which I mean it's so what is the algebraic monodromy? Well, this Betty local system corresponds to some representation of the fundamental group into sort of GL of a fiber of this local system. That's not. Okay, and the algebraic monodromy is take the image of this representation and take the Zariski quotient. Sorry, other things are organized here because I wanted to keep this remark. But is hopefully this is clear. Yeah.
Is it really a statement about motives, or is somehow arbitrary by that?
I'll come to that. The answer is yes. It is more or less a statement about sort of. Anyway, I'll come to that. Okay, so that's just the algebraic monodromy group, just for future, so I don't have to keep writing algemon. Let me just use the notation G sub, if I have a local system B, G sub B is going to be the algebraic monodromy. Okay, now the reason I wanted to leave this remark is that actually they prove this enhanced, the functional analog of this enhancement. It has a similar feel to it. Again, it's saying that the only relations on these functions are the ones coming from sort of push-pull of families, or Stokes theorem, or now sort of the relations coming from constant families. Cool. Okay, so now what is the Andre version? Sort of theorem one. Oh, I should have said this is all joint work with Jacob Tsimerman. Okay, so what's the appropriate analog here? Well, we somehow, in the functional analog where our base field Q is being replaced with the function field of this algebraic variety, K. Okay, so now we want to sort of consider some field L that sits between K and this field of meromorphic functions on germs of meromorphic functions on S. Right? So we still want to take a motive over L, and the statement is the same, except now we're taking the relative motivic L logarithm. Okay, no, so now I know the correct, so that the L should have been there in the previous. Obviously here, what I want to do is take motives over L and look at the base change on the previous motivic L logarithm that I had should have been. Okay, so that's the statement. So there's a slight a subtlety here that if we don't interpret correctly, it's going to make this theorem kind of trivial. And that is, what actually do I mean about the periods of M? So, again, if we think of M as coming from a family of algebraic varieties, then these periods are just these functions I obtain by sort of integrating algebraic Durand classes against flat families of cycles. Okay, so they're holomorphic functions on S for germ holomorphic.
So, I mean, there's something, this K, you mean you mean that S is not compact and you take meromorphic functions?
Right.
This is not what you wrote, however.
Well, I mean, it's enough to consider, germs at a point.
There's no ring of which you're taking
What do you mean?
What is it?
Sorry?
the local ring is just algebraic, so you get the rational functions and not the meromorphic functions.
No, you're taking the stock of the analytic structure sheet. Like germs of polymorphic function that is.
And what is S0? It's a generic point.
It's a generic point. So you're right that I'm allowed to shrink S. Like, what does this actually mean? So we do this in the paper. The correct way to think about this is you want to take like a small arc and not like an actual point. Because of course, if you have an actual point, then it might disappear if you go to a system. Like an arc will never disappear. Does that answer your question? Okay. Somehow, it's not going to matter for this field because.
Anyway, I understood what you meant.
Yeah. That's more of a technicality formulation. Anyway, okay, so the point is that these periods of M live in this field Kn, right? They're valued in Kn. Okay, so what does they should be valued in the same field over here, right? L is intermediate between K and Kn, and previously the periods valued in C. So the periods over here are valued in Kn, but somehow my family M is over L. So what does that actually mean? Okay, so what does this mean? Okay, well, again, K is the function field of some algebraic variety S. Okay. Now, we may as well restrict to L being the function field of an algebraic variety, because otherwise this left-hand side will be infinite. Okay. So this is a finitely generated field over K, which is therefore the function field of some other algebraic variety T.
Why is it you assume it's finite?
Well, I mean, this projection is kind of empty if the left-hand side is empty. All right.
So you assume it's finite.
I mean, I may as well assume that it's finitely generated, otherwise the conjecture, I mean, the theorem is clearly true. Oh, yes, sorry, thank you. The problem with not erasing the entire board, but superimposing. Okay, so what does this mean? Well, the embedding of K into L means I have a rational algebraic map from T to S. Okay, now the embedding of L into Kn means that upon analytification over some ball containing S naught, I have a section, right? Because then this embedding will just be pulled back along that analytic section. Okay, so now it's kind of clear what we mean by the periods of M, which is family over L, valued in polymorphic functions on S. It means we take the periods as a family over T and we pull them back by a tau. Okay, and then we adjoin those functions to L, and that's the transcendence degree that we're measuring. Okay, and that also sort of makes it clear why this is a generalization of this, because of course, you know, if you take the periods of M over T, they have so many algebraic relations. If you pull them back along this kind of random analytic section, they could satisfy more algebraic relations. And this theorem is saying, well, they don't actually satisfy that many more. We have control over how many algebraic relations. Okay, so how late did I start? This becomes a relevant question. Sorry?
You still have more than 20 minutes.
Oh, great. Okay, so now as Danny was suggesting, let's take, you know, these three boards and kind of upgrade one step further, and now just consider complex local systems that don't necessarily come from geometry. And so for now, going to be thinking, we still have S, a complex algebraic variety, and now we want to think about V, a complex local system. S on Sn. Okay, and we still have a sort of Betty realization and a Durand realization and a comparison. You know, the Betty realization is sort of tautologically just V. And the sort of Durand realization is the canonical algebraic structure on V. The canonical algebraic structure with regular singularities. Okay, so let's call that early V. The canonical algebraic structure on the sort of analytic flat vector bundle associated to V, which is just V tensor over CS OS. And we have a comparison, which we can't interpret as integration in general, but just says that if I tensor this algebraic guy over the analytic ring, I get this analytic vector bundle. And again, this is, you know, in the special case of a Gauss-Monnine connection, the canonical algebraic structure is exactly algebraic Durand homology. Okay. So we can kind of try to play the same game as we did over here, which I want to do, but I want to simultaneously kind of make this statement a lot more geometric. Like as it stands, the statement about sort of transcendence degree of some functions, it would be nice to have a purely geometric formulation. Okay, so let's try to do that. Okay, so the relevant thing to do here is to consider I the sort of space of comparisons. By which I mean, you know, a point in S together with an isomorphism on the level of fibers from this curly V to this the fiber of the local system at S naught. This is somehow not the stock, this is the fiber. And you know, this is an algebraic structure. I mean, this lives in like the geometric total space of just the vector bundle of Helms from curly V into VS naught tensor OS. The trivial vector bundle. Yeah, so this is some algebraic variety parameterizing these sort of comparisons between some random fiber of V and this fixed fiber of Roman V. Okay, and this also has a flat connection coming from the flat connection of these two guys. I can just transport a comparison with respect to the flat connection on B. But treat this as a constant vector. Okay, now, if we analyze, so obviously this maps down to S, so that map pi. If we analytify, I claim that this has a natural section, at least over the universal cover. Okay, what is the section? Well, it needs to associate a point in S together with a homotopy class of paths from S naught to S, a comparison, take the parallel transport. Parallel transport map. Parallel transport along that homotopy class paths with respect to the flat connection. Okay, and this sort of gives me some analytic subset of the analytification of I. So let's give it a name. Let me call sigma B the image of sigma. Okay, now what does this thing look like? Okay, well, you have a particular comparison. What do the fibers of this thing look like? Like over a particular point in S, we're getting all comparisons that arise, from one parallel transport to S, composed with sort of all other parallel transports on loops based at S. So the fiber of the image of this over a particular point is just some conjugate of the image of the monodromic representation. Fibers on sigma V are just the sort of image, again, conjugates of the image of this monodromic representation. Conjugates. Right? Because again, the set-wise, like over a point S, I'm just getting all parallel transport operators, to S. Right? So that's just a conjugate, take the image of the monodromy representation and conjugate by your favorite choice of parallel transport from S naught to S. I should have said this before, that this space has some additional structure because it obviously has an action by GL PS naught, just by post composition, which makes this a torsor over S, a torsor for GL PS. It's naturally sort of an algebraic flat principal bundle for GLBS naught. We have this analytic section over the universal cover, and the sort of fibers are just conjugates of the Okay, so let me actually leave this statement up here. And let me call, the natural thing to do now is to take omega V to be the Zariski closure of sigma V. So this is now an algebraic subvariety. It lives over S. Now, the fibers we said were conjugates of the image of the monodromic representation. So the Zariski closure of a fiber is a conjugate of the algebraic monodromy. Okay. But, taking the Zariski closure and then taking a fiber is different from taking a fiber and then taking the Zariski closure. So the fibers of the Zariski closure here could in principle be bigger. Okay? But I at least have like an action by the algebraic monodromy group. Okay? And this theorem is exactly saying that in fact the fibers are precisely the orbits under GB. In other words, that this is a principal GB bundle. Okay, so why is that? Well, the transcendence degree of K adjoins the periods of M, let's think about what that is. In the algebraic coordinates on this space I are just the matrix of this comparison with respect to an algebraic frame on the source and this constant, namely flat frame on the target. Okay. So the algebraic coordinates here are exactly periods. So the change of basis matrix from the algebraic frame to the flat frame. And so this transcendence degree is exactly the dimension of omega B, That's the transcendence degree of this over C, and then minus the dimension of the base. And we see that if this difference of dimension, remember that this is equal to the motivic logarithm. So, if we have this equality of dimensions, it means that in fact the fibers of the full Zariski closure are the same as the Zariski closure of the fibers, and that this is a principal GB bond. Okay, so this fact, so this being omega V being a principal GB bundle or whatever, a GB torsor is the same as this. Okay, this is in fact, one way to prove this. Nori proves this. You can show that this is in fact, you can basically using the functoriality of the canonical algebraic structure, you can show that this Zariski closure is exactly just the unions of the fibroblasts. Okay, and maybe one other note I'll make is that, I had this remark that there's sort of an enhancement due to Concevic-Xavier. That translates into this omega V being connected, which is also clear in this context because we're taking the Zariski closure of an analytically connected space, algebraically connected. Okay, so sort of from this picture, you can deduce, this theorem of the Nori together with that enhancement that I had mentioned. Okay, so got a fourth board. Okay, I don't want to erase that. So now let me unfortunately, I think I'm going to have to erase it. But hopefully maybe I'll just erase this and keep this. Maybe I'll do the reverse. Fine, I'll erase the whole thing, so I don't have to choose. So now, purely in terms of the geometry of this sort of period torsor, you should think of this as sort of the torsor of comparisons between the sort of Durand realization of this flat bundle and the Betty realization. Let's write down an atypical intersection statement. Okay, so it's going to look like it has nothing to do with theorem 1, but in fact it's going to be equivalent to theorem 1. Okay, so what does it say? It says so this is theorem 2. It says that if V is a local system underlying an integral variation of mixed Hodge structures, suppose we have the following setup. We have an algebraic variety of this period torsor omega V. Okay, and suppose U is a component of the intersection with this with the sigma V, this sort of locus of parallel transport operators. W intersects. Yeah, so there's some analytic subset of the intersection, right? And suppose that it's a component that's bigger than you would expect. And so typically, sigma V has codimension in omega V, exactly the dimension of GV, right? Because the fibers of sigma V are discrete. Or whatever, zero dimensional. So you would expect that the codimension, such that you would expect the codimension of U inside W to just be equal to GB. Okay, so the atypical situation is when it's bigger than expected. So let's assume that the codimension here is smaller than GB. Okay, then the theorem says in sort of the typical yoga of atypical intersections is that if you have an atypical intersection, it's happening for a reason. And in this context, the reason is if I have some kind of atypical intersection, it has to be because if I restrict the local system to the Zariski closure of the projection of U downstairs, I must have strictly smaller algebraic model. So the dimension, it's going to be a little complicated, the algebraic monodromy of V when I restrict to the projection of this U and then take the Zariski closure, some subvariety of S, so I can restrict V to it. That's some local system on here. I can take its algebraic monodromy. I want this to be strictly smaller than the algebraic monodromy that I start with. I just parenthetically say that, in particular, the projection of U is non-Zariski dense. Somehow we're saying not only if you have an atypical intersection, it sort of can't be happening generically along S, but even more than that, we can sort of have control over the algebraic monodromy of the local system, restricted to the Zariski closure of that. Okay, what is this? We make some remarks. Okay, so remark 0, over here, we were kind of selling this as saying, the algebraic independence of these functions is controlled by geometry. Sort of, where's the geometry showing up here? Well, the point is that Hodge theory tells you that the algebraic monodromy of a variation of Hodge structures getting smaller exactly means more Hodge classes are here. Okay, so Hodge theory says that sort of smaller algebraic monodromy is like the same as more Hodge classes. Possibly in some tensor power. Okay, so really the conclusion, if you like, the conclusion here is that the algebraic monodromy reduces. Really what that means is that this U has to lie in some strictly smaller Hodge limits. Okay. The second remark, the interesting remark, is I'll leave this as an exercise, and it's a fun exercise. It's just kind of playing around with the statements here. So the exercise is that, as I was saying, at least for if you look at integral variations of mixed Hodge structures that come from geometry, theorem 1 and theorem 2 are equivalent. At least for the VMHS coming from geometry. Theorem 1 are the same. Okay, so like I said, this is kind of an easy, fun exercise. It's not obvious, but there's kind of one non-trivial step that I want to say something about, and that's the step in deducing theorem 2 from theorem 1. Okay? And because somehow the setup is a little different. The setup in theorem 1 is we have T over S and we have some family over T. We're taking the periods of T and sort of pulling them back. But over here, we just have this local system sort of over S. There isn't like a T over S or something. So how do we go back and forth? Okay, well, let me give you sort of the hints for this exercise. And the hint is for theorem 1 implying theorem 2. The other direction is more straightforward. But the point is that we have this period torser, and it maps down to S, and we have this atypical intersection. We get this P of the projection of U is some subset of S. Now the point is that well, we can find some algebraic projection of S, let's say to an affine space, dimension capital N, for which the restriction to this analytic set is generically finite. So generically finite means generically eternal, and therefore over some ball in here I have a section. There's some ball here over which I have a section. Okay, so now I'm exactly in that situation. So if I apply this theorem to sort of this V family over S, I mean, the letters are different. This S is that T, this AN is that S. if you apply that statement, this picture, you will conclude this statement. And like I said, it's not once you sort of realize that, then it's just kind of a fun exercise. Okay, now that I've said that they're equivalent, I can maybe erase one of the two there. Let me erase this one. The second remark is that this sort of, there's been in the past 10 years, sort of people have systematically been proving atypical intersection sort of statements like this for variations of Hodge structures, usually called the Ax Schanuel conjecture for various things. This is a version of the Ax Schanuel. And I want to say that sort of this theorem implies sort of all other. It's kind of the universal Ax Schanuel for variations of Hodge structures. So theorem 2 implies all other Hodge theoretic Ax Schanuel statements. And I can tell you maybe after the talk sort of how to formally deduce them, but let me just kind of give an idea for why this should be true. So let me give an example. So suppose we have like n elliptic curves, families of elliptic curves over S. Let's suppose each one comes with a section, or pi. And let's also suppose that on each elliptic curve, I give a holomorphic, an algebraic form which restricts to whatever, just a holomorphic form on the total space. So omega I, one form. Okay, so the pure Ax Schanuel in this context, which was proven by Montpellier and Tsimerman for shorter varieties, and then myself and Jacob for pure variations of Hodge structures, basically says, it's a transcendence statement for the coordinates of the associated pure variations of Hodge structures. Okay, so what are those coordinates? Well, we know what those coordinates are. It's just you form the functions tau I, which is kind of the ratio of the periods. Okay, so here, alpha and beta are, as usual, some symplectic basis for homology, and you form this ratio of integrals. And what Ax Schanuel says in this context is, well, you have n functions here, okay? If the transcendence degree is smaller than n minus m on U in S, some analytic subset of S, of, let me say Sn, of codimension smaller than m, so it's it's easy to make the transcendence degree drop by m over a codimension m locus, but here the locus is sort of bigger than you would expect. Then it must be for some reason, and in this case, the reason is that some of the EIs are either S-trivial or S-isogenious. And what is the mixed statement here? How much time do I have left now? How many minutes?
2 minutes.
2 minutes? Okay, great. Okay, so what is the mixed statement? Which was proven for the universal family of abelian varieties by Gao, and then in general for mixed variations by Chu and independently by Gao. It says, well, we do the same thing, but now we take sort of the coordinates of the variation of mixed Hodge structure instead of, maybe shows up here. So we could take, for instance, the relative cohomology, like E, comma, the subset 0 pi, okay? So then we have two n functions. We still have the tau i's, but now we have a new function, which is just the integral of a sort of a relative period of the omega i's. So here, gamma I, should I draw this picture? Maybe this is alpha I, this is beta I, and gamma I is a path from like 0 to pi. Okay, so now we have these functions, and if their transcendence degree is smaller than or equal to 2n minus m, but still over an analytic locus of codimension less than m, then again, it must be for a reason. And either it's this reason, one way the transcendence can drop, or the other way the transcendence can drop is if the sections are torsion, or PI are torsion. Okay, and this is where I'll end. Finally, the sort of version for the period torsor, so theorem 2, is saying, well, rather than, from the perspective of period integrals, we're taking these kind of weird ratios that arise from like flag coordinates for the Hodge filtration. And this theorem is basically saying just directly look at the period. So this period version says that if you just take these 3 n functions, so now you have 3 n functions, and you ask that the transcendence degree, be less than or equal to 3n minus m, again on an analytic locus of bigger than you would expect. Then it must be for a reason, and well, we've already written the 2 possible reasons. So it's either this one or it's this one. The conclusion is either star or. Okay, so I'm probably out of time. Let me just say in like the last 10 seconds, the last remark was going to be, we give sort of 2 proofs of this theorem 2, which then implies theorem 1. So one proof is sort of in the same spirit as all the other proofs that I've listed here using omenability and Peele-Wilkie. And then the second proof is actually is in some sense a corollary of some more recent work of Blazkis-Sans, Saul, Freytag, and Naglu on transcendence, Ax Schanuel type statements for principal bundles. So exactly the kind of situation we're in, that only uses complex geometry. Okay, so there's no omenability there, which is, I find, both awesome and amusing because, 2 of those authors are omenabilists. Somehow they, beat us at our own game. Anyway, let me stop there.